Chapter 9. Standards and Approvals.
Next, we turn to valve standards.
I would like to introduce the overall picture of control valve standards. Numerous standards are applied to control valves, and international and global standards are becoming increasingly important, especially for companies participating in global markets. These standards are not merely reference documents. They serve as direct criteria in the process of designing control valves and applying them to actual processes. In this chapter, we will organize the codes and standards that have been or will be important for the design and application of control valves, categorized by their issuing organizations.
I will introduce the control valve standards from the American Petroleum Institute, API, and the American Society of Mechanical Engineers, ASME. From API, Spec 6D covers pipeline valves such as gate, plug, ball, and check valves. 598 covers valve inspection and testing. 607 specifies fire tests for soft-seated quarter-turn valves. And 609 regulates lug and wafer-type butterfly valves. From ASME, B16.1 covers cast iron pipe flanges. B16.4 covers gray iron threaded fittings. And B16.5 covers pipe flanges for steel and nickel-based alloys. B16.10 deals with face-to-face and end-to-end dimensions of valves, though dimensions for most control valves refer to ISA standards. Continuing on, B16.24 covers copper alloy flanges. B16.25 covers but welding ends. B16.34 covers flanged, threaded, and welding end valves. B16.42 covers ductile iron pipe flanges. And B16.47 regulates large diameter steel flanges from NPS 26 to NPS 60.
I will introduce the Industrial Valve Standards from the European Committee for Standardization, CEN. EN 19 covers marking. Part of EN 558 specifies face-to-face and center-to-face dimensions for PN-designated valves, and Part 2 covers the same dimensions for class-designated valves. EN 593 is for butterfly valves, and EN 736 covers valve types in Part 1, components in Part 2, and definition of terms in Part 3, with Part 3 currently in preparation. EN 1349 for industrial process control valves is also in preparation, and part of EN 12266, which covers testing of valves, test procedures, and acceptance criteria, is likewise in preparation. EN 12516 deals with shell design strength, divided into the tabulation method for steel valves in Part 1, the calculation method in Part 2, and the experimental method in Part 3, all of which are in preparation. Additionally, EN 12627 covers butt weld end design, EN 12760 covers socket weld end design, and EN 12982 covers end-to-end dimensions for butt welding end valves, all of which are currently in preparation.
Next, I will introduce the European Material and Flange Standards. EN 12183 covers the technical conditions for the delivery of steel castings for pressure purposes, with Part 1 covering general requirements, Part 2 covering steel grades for use at room and elevated temperatures, Part 3 covering steel grades for use at low temperatures, and Part 4 covering austenitic and austenoferritic steel grades. EN 12212 covers the delivery conditions for steel forgings for pressure purposes, with Part 2 covering ferritic and martensitic steels for use at elevated temperatures, Part 3 covering nickel steel for low temperatures, Part 4 covering fine-grained steel, and Part 5 covering austenitic, martensitic, and austenoferritic stainless steel. Regarding flanges, Part 1 of EN 1092 covers PN-designated steel flanges, and Part 2 covers PN-designated cast iron flanges, while Part 1 of EN 1759 for class-designated steel flanges is currently in preparation. Finally, FCI 70-2-1991 specifies the control valve seat leakage.
I will now introduce the control valve standards from the Instrument Society of America, ISA. S51.1 covers process instrumentation terminology. S75.01 covers flow equations for sizing control valves. S75.02 covers capacity test procedures, and S75.14 covers terminology. Regarding face-to-face dimensions, S75.03 specifies flanged globe-style bodies for classes 125, 150, 250, 300, and 600. S75.04 specifies flangeless valves for classes 150, 300, and 600. And S75.16 specifies flanged globe-style bodies for classes 900, 1500, and 2500. For noise, S75.07 covers the laboratory measurement of aerodynamic noise, and S75.39 covers the aerodynamic noise prediction method. Additionally, S75.17 covers inherent flow characteristics and rangeability. S75.25 covers the method of evaluating the performance of positioners with analog input signals. S75.40 covers the hydrostatic testing of control valves, and RP75.23 covers considerations for evaluating control valve cavitation.
I will introduce ISA's additional face-to-face dimension standards and an overview of the IEC. S75.08 covers the installed face-to-face dimensions of flanged clamp or pinch valves. S75.12 specifies the dimensions for socket weld-end and screwed-end globe-style valves from class 150 to 2500. S75.14 covers butt-weld-end globe-style valves for class 4500. And S75.15 defines butt-weld-end globe-style valves from class 150 to 2500. S75.20 covers separable flanged globe-style valves for classes 150, 300, and 600, and S75.22 covers the face-to-centerline dimensions for flanged globe-style angle valve bodies of the same classes. A significant number of control valve standards from the International Electrotechnical Commission, or IEC, are based on ISA standards.
I'll explain the status and adoption trends of IEC standards. Many IEC standards have been republished as YEN standards and use the YEN prefix. The IEC encourages national committees to adopt these standards and to withdraw any corresponding national standards. As a result, both manufacturers and purchasers are increasingly applying IEC standards. The standards for industrial process control valves are organized into the 60534 series, and we will cover the detailed parts in the following slides.
I will introduce the first part of the IEC 60534 series. Part 1 covers control valve terminology and general considerations. Part 221 covers sizing equations for incompressible fluid flow under installed conditions as part of flow capacity, and is based on ISA as 75.01. Part 223 covers test procedures based on ISA as 75.02, and Part 224 covers inherent flow characteristics and rangeability based on ISA as 75.11. Part 4 covers inspection and routine testing. Part 5 covers marking, and Part 6-1 covers mounting details for the attachment of positioners to control valve actuators, specifically for positioner mounting on linear actuators.
I'd like to introduce the remaining items of the IEC 60534 series and other international standards. 60534-6-2 specifies the details for mounting positioners on rotary actuators, and 60534-7 defines the control valve datasheet. The 60534-8 series dealing with noise is divided into 4 parts. 8-1 covers laboratory measurement of aerodynamic noise based on ISA 75.07, 8-2 covers hydrodynamic noise measurement, 8-3 covers aerodynamic noise prediction based on ISA 75.17, and 8-4 covers hydrodynamic noise prediction. From ISO 5752 covers face-to-face and center-to-face dimensions, and the 7005 series specifies steel, cast iron, and copper alloy flanges. For MSS, SP6 covers contact face finishes, SP25 covers marking for valves and fittings, SP44 covers steel pipeline flanges, and SP67 and 68 cover butterfly valves and high-pressure offset butterfly valves. Finally, NACE International's MR0175, ISO 15156, and MR0103 specify metallic materials for use in H2S, containing environments, namely sulfide stress corrosion cracking environments. Next, we will move on to the topic of product approvals for hazardous classified locations.
Next, we turn to hazardous areas.
I would like to introduce the standards applied to electrical equipment used in hazardous classified locations. CSA C22.1 refers to the Canadian Electrical Code, or CEC, and C22.2 number 94, and 91 covers special industrial enclosures. Yen 60,000 and 79-0 from Senelec, the European Committee for Electrotechnical Standardization, specifies the general requirements for electrical apparatus for potentially explosive atmospheres. ISA S 12.1 contains definitions and information pertaining to electrical instruments installed in hazardous classified locations. From the IEC, 60,000 and 79-4 covers electrical apparatus for explosive gas atmospheres, and Part 4 specifies the method of test for ignition temperature. Together, these standards form the foundation of the system that ensures equipment for hazardous locations receives appropriate approval from recognized approval agencies.
I would like to introduce the standards related to enclosure protection and the approval system in North America. IEC 60529 specifies how to indicate the degree of protection provided by enclosures using the IP code. NEMA 250 in the U.S. covers enclosures for electrical equipment up to 1,000 volts, and NFPA 70 is the National Electrical Code, or NEC. NFPA 497M covers the classification of gases, vapors, and dust for electrical equipment in hazardous classified locations. Both the NEC in the U.S. and the CEC in Canada require that electrical equipment used in hazardous locations carry appropriate approval from a recognized approval agency. The three main approval agencies in North America are Factory Mutual, or FM, and Underwriters Laboratories, or UL, in the United States, and the CSA in Canada.
I would like to introduce two of the protection types commonly used for instruments in North America. The first is dust ignition proof. This type of protection excludes ignitable amounts of dust, or amounts that might affect performance or rating, from entering the enclosure. When installed and protected in accordance with the original design intent, it ensures that arcs, sparks, or heat generated or liberated inside the enclosure will not cause ignition of exterior accumulations or atmospheric suspensions of a specified dust. The second is explosion proof. This type utilizes an enclosure capable of withstanding an explosion of a gas or vapor within it, and preventing the ignition of an explosive gas or vapor that may surround it, while maintaining an external surface temperature low enough that surrounding explosive gas or vapor will not be ignited.
Continuing with North American protection types, I would like to introduce intrinsically safe and non-incentive protection. Intrinsically safe protection is a type where electrical equipment, under both normal and abnormal conditions, is incapable of releasing sufficient electrical or thermal energy to cause ignition of a specific hazardous atmospheric mixture in its most easily ignitable concentration. In other words, the energy level itself is limited to be below the ignition threshold. Non-incentive protection is a type where the equipment is incapable, under normal conditions, of causing ignition of a specified flammable gas or vapor and air mixture due to arcing or thermal effects. The key difference between the two is that while intrinsically safe covers both normal and abnormal conditions, non-incentive is based on normal conditions.
Next, we turn to NA classification.
I would like to introduce the system used by North American approval agencies to classify equipment for hazardous locations. When classifying equipment for use in hazardous locations, North American approval agencies designate the location as Class 1 or 2. Division 1 or 2, Groups A, B, C, D, E, F, or G, and temperature code T1 through T6. The class indicates the general nature of the hazardous material. The division indicates the probability that an ignitable concentration is present. The group indicates the specific hazardous material, and the temperature code indicates the maximum surface temperature rating. These designations are defined in the NEC and CEC. Therefore, a single approval consists of a combination of the protection type along with the class, division, group, and temperature. For example, Class 1, Division 1, Groups A, B, C, D, T6.
I would like to introduce how hazardous locations are classified. In North America, hazardous areas are divided into three main axes. First is the class, which defines the general nature of the hazardous materials present in the surrounding atmosphere. Second is the division, which indicates the probability that those hazardous materials actually exist in an ignitable concentration. Third is the group, which defines the specific type of hazardous material in the atmosphere. One point to note is that the method of classifying locations as zones instead of divisions was introduced as an alternative in the 1996 edition of the NEC. However, this zone system is not yet practically used in North America, and is generally used in Europe and most other countries.
I'll start by explaining the class in detail. Class 1 refers to locations in which flammable gases or vapors are, or may be, present in the air in quantities sufficient to produce explosive or ignitable mixtures. Class 2 refers to locations that are hazardous because of the presence of combustible dusts. Class 3 refers to locations in which easily ignitable fibers or flyings may be present, but are not likely to be in suspension in sufficient quantities to produce ignitable mixtures. Next, the division defines the probability of these hazardous materials being present in an ignitable concentration in the surrounding atmosphere. For more detailed definitions, please refer to the ISA S12.1 standard.
Let's break down the division into two types. Division 1 refers to locations in which the probability of the atmosphere being hazardous is high due to flammable material being present continuously, intermittently, or periodically. Division 2 refers to locations that are presumed to be hazardous only in an abnormal situation. Next, the group defines the hazardous material in the surrounding atmosphere. The specific materials for each group and their automatic ignition temperatures can be found in NEC Article 500 and NFPA 497M. Groups A, B, C, and D apply to Class 1 locations, while Groups E, F, and G apply to Class 2 locations. The following definitions are taken from the NEC. Group A refers to atmospheres containing acetylene.
I'll summarize the representative materials for each group. Group B includes atmospheres containing hydrogen, fuel, and combustible process gases containing more than 30% hydrogen by volume, and gases or vapors of equivalent hazards such as butadiene, ethylene oxide, propylene oxide, and acrolein. Group C includes atmospheres such as ethyl ether, ethylene, or gases or vapors of equivalent hazard. Group D has the broadest range, including atmospheres such as acetone, ammonia, benzene, butane, cyclopropane, ethanol, gasoline, hexane, methanol, methane, natural gas, naphtha, propane, and equivalent hazard materials. Group E refers to atmospheres containing combustible metal dusts, including aluminum, magnesium, and their commercial alloys, or other combustible dusts whose particle size, abrasiveness, and conductivity present similar hazards when using electrical equipment.
I'll explain the remaining dust groups and the concept of the temperature code. Group F refers to atmospheres containing combustible carbonaceous dusts, such as carbon black, charcoal, and coal, or dusts that have been sensitized by other materials to present an explosion hazard. Group G refers to atmospheres containing combustible dusts not included in Group E or F, such as flour, grain, wood, plastic, and chemicals. Now let's look at the temperature code. A mixture of hazardous gases and air may be ignited by coming into contact with a hot surface. The conditions under which a hot surface will ignite a gas depend on the surface area, temperature, and the concentration of the gas. Therefore, approval agencies test various pieces of equipment submitted for approval to establish their maximum temperature ratings.
Finally, I'll explain how temperature codes are assigned and labeled. Equipment that passes the test receives a temperature code that indicates the maximum surface temperature attained by the equipment. A typical North American approval marking consists of 4 parts. For example, let's look at the marking Class 1, Division 1, Groups A, B, C, D, T4. The Class 1 part is the hazard type, and Division 1 is the area classification. Groups A, B, C, D refers to the gas or dust group, and finally, T4 is the temperature code, a value based on the North American temperature code system. By reading these 4 items together, you can tell at a glance which hazardous environments the equipment is suitable for.
Next, we turn to enclosure ratings.
I'd like to introduce the temperature code system and enclosure ratings for explosion-proof equipment. Temperature codes are subdivided into T1, T2, T2A, T2B, T2C, T2D, T3, T3A, T3B, T3C, T4, T4A, T5, and T6, with a maximum allowable surface temperature defined in Celsius and Fahrenheit for each code. According to NEC regulations, equipment with a maximum surface temperature not exceeding 100 degrees Celsius, 212 degrees Fahrenheit, based on an ambient temperature of 40 degrees Celsius, 104 degrees Fahrenheit, is not required to be marked with a temperature code. Therefore, if a temperature code is not specified on approved apparatus, it is assumed to be T5. The temperature code indicates the actual maximum surface temperature the device reached during testing. Meanwhile, enclosure ratings are determined by testing the ability to prevent the ingress of liquids and dusts. In the United States, equipment is tested to NEMA 250. In the following section, I will summarize the representative enclosure ratings defined in NEMA 250.
I'd like to introduce the NEMA Type 3 series enclosures used in general locations. Type 3 is an outdoor enclosure with dust-tight, rain-tight, and ice resistance properties, primarily intended to protect equipment from rain, sleet, wind-blown dust, and damage from external ice formation. Type 3R is an outdoor enclosure with rainproof and ice resistance functions. The difference from Type 3 is that it protects against rain, sleet, and external ice damage, but does not include protection against wind-blown dust. Type 3S is characterized by being dust-tight and rain-tight, and it further ensures that external mechanisms operate normally even in icing conditions. All three ratings are primarily intended for outdoor use and are distinguished by whether they protect against wind-blown dust and whether they guarantee mechanism operation during icing.
I'd like to introduce NEMA Type 4 and Type 4X enclosures. Type 4 is an indoor-outdoor enclosure with watertight, dust-tight, and ice-resistant properties, protecting equipment from wind-blown dust and rain, splashing water, hose-directed water, and damage from external ice formation. The key difference is that Type 4X adds protection against corrosion to these performance features. Both ratings can be used both indoors and outdoors, and they share common protection against wind-blown dust, rain, splashing water, hose-directed water, and external ice. Therefore, Type 4X should be selected for environments with corrosive atmospheres.
I'd like to introduce NEMA enclosures used in hazardous, classified locations. There are 4 NEMA enclosure ratings for hazardous locations, 2 of which are described in NEMA 250. The first is Type 7, which is an enclosure for indoor hazardous locations corresponding to Class 1, Division 1, Groups A, B, C, or D. It is intended for indoor use in Class 1, Division 1, Groups A through D as defined in the NEC, and the class, division, and group must be marked on the enclosure. Type 7 enclosures must be capable of withstanding the pressures resulting from an internal explosion of specified gases and contain such an explosion sufficiently so that an explosive gas-air mixture in the surrounding atmosphere will not be ignited.
I'd like to introduce Type 9 enclosures and the practice of labeling enclosure ratings. Type 9 is an enclosure for indoor hazardous locations corresponding to Class 2, Division 1, Groups E, F, and G. It follows the classifications defined in the NEC and is intended to prevent the entrance of dust. Similarly, the class, division, and group must be marked on the enclosure. However, these 2 NEMA ratings are often misunderstood. For example, the definition of Type 7 is essentially the same as the definition of explosion-proof. Therefore, if an approval agency certifies a piece of equipment as explosion-proof and suitable for Class 1, Division 1, that equipment automatically satisfies the Type 7 requirement. However, the agency does not require the equipment to be labeled as Type 7. Instead, it is labeled as suitable for Class 1, Division 1. Similarly, Type 9 enclosures are labeled as suitable for Class 2, Division 1.